Thank you very much, and I would like to thank the organizers of this conference for giving me this opportunity to present a perspective on thermochemical conversion in restoring woodlands and our forest. So I'll just start with some background, and this is actually a snapshot of our lab at Utah State, which is located at Innovation Campus here. And as a student, I've been working in the area of thermochemical conversion using pyrolysis and low temperature gasification to convert woody biomass, herbaceous feedstocks, and even animal waste. Up in Virginia, we do have a transportable 100-pound-an-hour unit that is on a farm, and we use that to dispose of the waste, and in doing so, we produce crude oil and solid residue biochar, which we've used that as a slow-release fertilizer. And so that's just about what we do. And this is a 4-pound-an-hour pilot plant that we have at USU, and we also have a bench scale pyrolysis unit that can process from 200 gram to about 500 gram of solid biomass in an hour. So our focus basically has been to be able to produce some form of bio-oil that you can actually co-process with petroleum oil. So the goal is to actually get this into existing infrastructure to produce gasoline. So this is going to be the outline. I'll give a brief introduction and then a talk on the thermochemical conversions, and that involves the overview on gasification, pyrolysis. Then I'll end with some challenges and conclusions. And as we've already heard from our previous speakers, the utilization of forest residues in producing some form of energy is a strategic approach, because the truth of the matter is if you don't do that, then climate change and other circumstances will do that at a cost for you. Either the wildfire will come and you will have to spend money in them. So definitely it is a strategic approach. Whether it's the best way, I think, is a starting point. And I just listed a whole host of feedstocks, and simply to present the idea that thermochemical platforms are advantageous because it's not feedstock dependent like biochemical platform, whereby you have to use enzymes to convert the lignocellulosics into bioethanol. Some of the issues you have inhibition that can destroy the enzymes, but with thermochemical conversions, you can actually use anything. I would say that definitely the quality of the biomass is important, especially like the ash content, but overall, it's not feedstock dependent. So the main thermochemical conversions that we've used in our lab basically are based on, you have slow pyrolysis, and with slow pyrolysis, the main goal is to produce solid residue, and this has been existent for a very long time. That's the process that is being used to actually produce charcoal. And now we have fast, or you can say flash pyrolysis, and basically the goal is to produce liquid product. And then what you do is you thermally heat that in the absence of oxygen, and then you produce some form of oxygenates in a form of vapor that you can condense. And gasification, as we've already heard from our previous speakers, that is one of the routes you can use to produce vapors that actually can generate electricity. And then with gasification, you have it at elevated temperatures, and the goal is to produce gas. And definitely gasification, it's a combination of pyrolysis, because the initial reaction would have to go through pyrolysis to produce that, and then you have a combustion of the char to enhance. This is just to give you an overview of gasification, and our goal is to produce fuel, and what I mean is to be able to get methanol, methane, DME, that is dimethyl ether, and some hydrocarbon fuels using Fischer-Tropsch technology. And you can use gasification for cogeneration of electricity, and the previous speakers has already they've touched on that, so I wouldn't emphasize much of that. And depending on your oxidant, you'll be able to produce different compositions that will direct the synthesis of these fuels. So I've just listed some of them, and this is the hydrogen to CO ratios, and that is important in terms of the quality of the syngas. This is just to give you an overview of some of the gasifiers that are available and the scale. Generally, we have fixed bed or moving beds, and that is either the updraft, downdraft, or the cross draft, and that is at a scale of 0.5 to 5 megawatts, and that is pretty small. Fluidized bed reactors, including bubble and circulating, another type of gasifiers, and you're looking at a scale of around 5 to 100. And then the biggest in terms of the output is the entrain flow gasifiers. We also have other types like the rotary kiln and combined pyrolysis and gasification units. And the next slide will just look at the advantages and some of the disadvantages. And so for biomass gasification, fluidized bed at the moment has been proven to be an effective reactor, because with that you don't have a limitation in terms of the fuel preparation. For instance, with a fixed bed, it has just a limited tolerance for fines. You would have to use coarse materials for that. And also, if you look at the entrain flow, it is also limited because it has a poor tolerance for coarse biomass. But overall, the entrain flow can produce syngas that has low tar content. And I'll talk about tar, which is one of the issues that affect the synthesis of the hydrogen and CO into other fuels. And so that's just about that. So applications. We know that you can gasify the biomass to produce electricity, and you can also use that to produce some form of fuels. And as I already mentioned, you can get methane, methanol, DME, and hydrocarbon fuels by Fischer-Tropsch. And this table is just giving you an idea of some of the operating conditions that you use to produce these form of fuels. And as you can tell from the syngas quality, for methane, you need to have an hydrogen to CO ratio about 3 to 1. For methanol, it has to be about 2 to 1. And then from DME, you have 1 to 1. And then Fischer-Tropsch hydrocarbons, you're looking at 2 to 1. And the particulate content and the tar content really matters in the synthesis of these products. For syngas production, we're looking at particulate around 0.02, and for tar content, you're looking at 0.1. If you're just doing direct combustion just to produce electricity or steam, it doesn't really matter. There's no limitation. So basically, the quality of the gas or the syngas, it depends on the applications, but our emphasis is more on producing these products. So syngas cleanup is one of the important stage in the production of those fuels in terms of DME, methane, methanol, and FT hydrocarbons. You can either do this two ways. It can either be in situ or post gasification. So with in situ, you end up with a tar-free product, and then what is left is your dust cleanup, and then you can get the clean gas that can now go into an FT synthesis. And then with post-gasification, you have your product with the tar, then it will go through some downstream processing to clean up, and then before you can do your FT synthesis. So what is tar? Tar is just a complex mixture of condensable hydrocarbons, and you have polyaromatic compounds and 1,2,5 ring aromatic as well, and some oxygenates. And with in-situ gas cleanup, you can actually achieve that by controlling the operating conditions, that is temperature, pressure, residence time. And for fluidized bed reactors also, you can use a catalyst as a bed, and then with that you'll be able to do some form of tar cracking with that. And then with post-gasification, you can either do thermal cracking, which is at a high temperature, or catalytic cracking, which is at a moderate temperature, and that is more of tar reforming. And then the last stage is more of the scrubbing of the gas and the separation and filtering, and that actually can be done at low temperature. So this is just a brief overview. I'll just change course over here and talk about pyrolysis. Pyrolysis, as I already mentioned at the beginning, is one of the routes that you can use to produce energy, and the focus here is to produce liquid product. And you do that in the absence of oxygen at a moderate temperature of about 500 degrees C, and that happens rapidly, less than 5 seconds. You produce some vapors. Some of them are non-condensable, and the non-condensable mixtures, you have CO2, CO, and methane, and some light hydrocarbons. Then the condensable come in the form of this dark brown liquid, smoky odor, and basically what you can do with this oil is as a heating oil, and it can also be considered as a chemical feedstock, and you can extract some liquid smoke out of it. Currently, the only commercial unit that is in existence, that is by Ensign, they use that to produce chemicals and not in terms of transportation fuel, and they extract liquid smoke out of it. The solid residue biochar, as we all know it, you can use that as a soil amendment or as a slow release fertilizer, and that is dependent on the biomass, because if you take, it's not any biomass that you can use as a slow release fertilizer, but with our previous experiments we've used chicken litter, so that has NPK. So basically you have a biochar that is rich in phosphorus and potassium, and you can actually use that. Okay, so just some quality about the bio-oil. Yes, we can use thermochemical platform like pyrolysis to produce bio-oil, but it stops as a heating oil. You cannot actually go further in its application, and that's because of its properties. If you look at this table where you have these properties against heavy oil, you realize that the pH of any bio-oil averagely from woody biomass, it has a pH of about 2.5. But if you take a different biomass that is rich in nitrogenous compound, that can go up a little bit, and that's because of those nitrogenous compounds. They can go even up to neutral pH. But for woody biomass, your pH is around 2.5, and you realize that it's low in carbon, and also it has low energy content. And look at the density, which is around 1.2 as against 0.88. Any oil that goes into the refinery is being judged by what we say the API, gravity, and this can go to negative. It's not good, so it can never go into. And distillability is also important. You realize that with heavy oil, even at 340 degrees, you can distill up to 90% of that oil. If you compare that to pyrolysis oil, you can go up to 250. But what happens? You form 50% goes into solid. And that is because it's a complex mixture, it is unstable. So I've just summarized the qualities. It's highly acidic, low heating value, it's viscous, it's unstable, and it's also incompatible with petroleum feedstock. So what do we do? But before I talk about it, I just want to talk a little bit on some of the pyrolysis reactors that are currently in use. We have fixed bed and or moving bed, but most research labs are moving away from fixed beds. It's because it's not flexible. Currently, bubbling fluidized beds are the most used reactors in the studies of pyrolysis. And then we have others like spouted and circulating fluidized bed. Circulating fluidized bed is also because that is more of a pilot demonstrations type kind of reactor. But for small scales, bubbling is fine. And then you have the rotating cone, vortex, ablative, and we have agar and vacuum. These are all types of reactors that are being used. So I just want to talk about how we are addressing the quality of the bio-oil so that at least you'll be able to further process that into either a drop-in fuel or maybe as a blend stock, because we need to move beyond the heating oil stage. Currently, there are two main routes that you can use. You can either use hydrotreating or catalytic cracking. These are all processes that are being used in the oil refinery. It's nothing new. With hydrotreating, it requires higher pressure, hydrogen, and also some metal catalyst. The only issue with hydrotreating is it's costly because you have to put in nitrogen and you have to put it at high pressure. But it is an efficient process in trying to upgrade the pyrolysis oil and to produce hydrocarbon fuel out of it. Another method, as I mentioned, is catalytic cracking. With this, is assisted or with catalyst, and you can operate this at atmospheric pressure and moderate temperatures. And the only issue is catalyst deactivation. That is the shelf life of the catalyst. But it is a promising technology, and most of my work has been on catalytic cracking using zeolite type of catalyst to produce upgraded oil. This is just a snapshot to give you an idea of the type of catalyst that has been used in upgrading pyrolysis oil. ZSM5 is a favorite and is the most used, and it's a medium pore size zeolite. White zeolite is also another type of catalyst that back in the 1995 they started using that to upgrade pyrolysis oils. And the good thing with the white zeolite is that is the active ingredient that is used in the catalyst for FCC cracking in the oil refinery. So if we can apply white zeolite, for instance, in upgrading bio-oil, which means in the future you can actually co-process the pyrolysis oil with petroleum, because they will all together be processed with the white zeolite. So there is a big interest in trying to achieve that. And this is just a list of the characteristics of upgrading the bio-oil by catalytic cracking. What you do is you lower the bio-oil yield, and because this is just conservation of mass. You have a bio-oil that is highly rich in oxygenated compounds, and all you're doing is trying to remove oxygen to produce hydrocarbon fuel, so it ends up with a lower yield. Theoretically, you can get hydrocarbon yields just a little over 33%. So you can imagine your yield will drastically drop. But what you end up doing is the oil becomes stable, it's less acidic, less viscous, and the energy content is increased, and now you can actually process that with petroleum crude. And then it also serves as a high-value chemicals. We have been able to produce bio-oils via this route, and we've done blending of the bio-oil at 15%. with crude oil. We co-cracked it to produce gasoline, and that we've only done up to 25% of blending. And also we've been able to produce chemicals like phenols that we've used as a substitute for phenol formaldehyde resins. So you can actually do that. This is just a snapshot of bio-oil after upgrading. So that is the direction that our lab is just focusing on right now. This is just the last slide, and basically with all the thermochemical platforms, they all have some kind of challenge, and this web is showing you some of the challenges that kind of prevent moving from a lab scale to a commercial scale, or to a demonstration, then to industrialization. And one of the issues is feedstock. You're going to talk about cost, quality, logistics in getting to the biorefinery, and then the quality of the product, and also policies. And then we have intensive R&D sponsored research, mass conservation, how to minimize byproducts to enhance the yield of the main product, production cost, and also emissions. So these are all issues that kind of face the production of bio-oil. I just want to end here, and once again, thank you for your attention.